Okay, here we go. Right. Now we are done with the two shear forces. It's time to move on to the next one. That is this. Okay. The shear at C. Oops, sorry, I thought it was the highlight. At this location. So this one, I think it's more apparent because C is nowhere near the support. We're just going to have to let go the shear at C and see what happens. Okay, so the same way. Now, beam is like this. We have the roller here. We have the hinge here. And now we let go of the color that I used. Okay, that one. So we now let go of the shear here. Okay. Weird. Anyway, okay. So again, the same sign convention. To positive to the right goes down. So this is down. To the left goes up. So this goes up. Okay. So you can imagine what's going to happen, right? If this one goes down, again, it's another seesaw. Yeah. And he goes up. So it's pushes his portion up. So this one is slightly more straightforward than the shear at the support, okay? And this becomes the shape of the influence line. All right. So essentially, it's going to look like this. Let me try to use the same color. Okay, sorry. So here is this. Not straight enough. Okay, so use that to help a little bit. Oh, look at that. I mean, why does it move down? Okay, all right. And because, again, the change of shear here, you know, that is going to have to be equal to 1. And C is right at midspan, right? Here is 2 meters. Here's another 2 meters. So the only way you can have 1 here, that means this has to be 0.5 and that has to be minus 0.5. And using the similar triangle, this is 2, this is also 2, so here is 0.5. And then this becomes the influence line of shear at C. More straightforward. You have any question? All right. So that's it. We can now move on to the next one. Now it's the moment. MA, MB, and MC. Okay. MA. Now A is here, that point. The way that we allow moment at A to move freely is that by adding a hinge here. Okay, and again, the sign convention for the moment, the positive one is like this. Okay, so you can either view it as this, like this, or you can, if you are very good with the sign convention, to the right is this, to the left is this. See? So now when you apply the moment, this left portion, again, because of the hinge, so it becomes essentially just like the door panel. And it can move because the direction of the moment is in this direction. It's just trying to rotate this direction. So this door panel will move down. Okay. But for the right portion, again, we have all the restraints in place. So this moment cannot move the right portion at all, which means the influence line of the moment at A is essentially just this one. Okay. And the value you can calculate by just applying the unit load here and calculate MA. Okay. And here is 1. So MA here, because unfortunately, the length here is 1. So the moment is equal to 1. So that means this is -1. Okay. And this is the influence line of MA. And let us go back and look at the structure again. Here, when I have this unit load, when I place the unit load anywhere on the left side of A, point A can be bent, right? Now, essentially, there is moment at A. But when I move this unit load, I keep moving it, and now it goes beyond point A. Just look at the point A itself. Is there any moment at point A at all because there's no load on the left side?
No.
The unit is now gone away. And when you cut the free body diagram of this, there's nothing on it. So even though point A can move downward because you have the load on the right side, but A itself has no moment. So the influence line reflects the behavior of the structure in such a way as well. So you can see when your load is no longer on the left side of A, point A no longer has moment, and it shows on the influence line. So any question? Quiet. So is that clear? Maybe. Now let's move on to point B. Point B is the support itself, right? Here we go again with the support. Now we just add the hinge here at the support. And the positive moment is in this direction, right? To the right is counterclockwise, to the left is clockwise. So again, when you have the hinge there, this guy is free to come down. Right? But on the right side, on this piece, because you have the restraint on both locations again, it can't go up. So it has to remain 0. And therefore, your influence line now looks like this. Notice how similar in shape of the influence line of MB to that of MA. It's the same nature of the load. And when I want to know how much this is, I simply apply the unit load here and calculate MB. So my free body diagram would be 1, but this time this is 2 meters, right? And here moment is going to be equal to -2. And here is therefore -2. Where do you get that value from? It's from this free body diagram. Any question on this one?
No.
Okay, so let us go back up and see the beam again. Now this time we focus on B. So, okay, when I have the unit load here moving around between the free end and B, this will essentially cause me to have the overhanging beam ABC, right? When the load is here, there will be the negative moment at B due to this. But as soon as the unit load moves past point B into the internal span BD, when the load is there, now you look at this. You are essentially having a simple beam, right? Because this part has no load. So it just been rendered, you know, irrelevant to the structure because there's no load. So there's no moment. So as soon as your unit load moves past point B into the span BD, you are essentially having a simple beam. I can easily write it like this. With a moving load, moving, anywhere, right? So when you have this situation, how can you have moment at B? Because point B now becomes just a, roller support. Sorry, it should be, you guys are gonna go crazy, right? So let's, oops. Okay, right. A roller support, simple roller support like that cannot have moment, right? You know that all along from the second year. And again, the influence line reflects the moment at the support B, the way it's supposed to be. You can't have the moment at support B at all when the unit load moves inside because your beam becomes a simple beam. Any question? Let's move on to the last one. Now it's MC. So again, we add a hinge here with the sign convention. Where is it now? There. On the right is this. On the left is that. And you're not confused, right? When I say on the right, but I draw it on the left of the hinge because it's on the right of this free body diagram, It's on the right. And here is on the left. Okay? And so when you have that, goes up and your deflected shape is now going to look like that. And that. Interesting, right? So our shape is like that. So it means the influence line is going to look like this for a moment at C. Yeah. So what would be the value? The easiest way again to calculate is by applying the unit load here to me and calculate the moment at C. When I apply the unit load there, essentially what I have is here. This is 4 meters, right? And it's getting ugly. 4 meters. And my moment is P, which is 1. L is 4, PL over 4. So, unfortunately, it's equal to 1. So maybe you makes you confused. Okay, 1. And that means we can use a similar triangle, the same angle here. If this is 1, that is -1. Right? The ratio is not quite right, so it may look a little bit deceiving. Let me try to redraw this with a better scale. Help you.
Sorry. Shouldn't it be 1 multiplied by 4 and over 2? Because C is at the middle between B and D.
It's the formula is PL over 4, young man.
Oh, sorry.
Yeah, it's okay. It's okay. If you have this, that's P, that's L. If P is at midspan, the moment is PL over 4. Right?
Yes.
Don't want to use a formula, it's fine. You can just calculate the moment yourself, because here is 1, your reaction is 0.5, right? So moment at midspan is 0.5 multiplied by 2, right? So it's 1. I just use the formula because I'm so used to it. So let us go back to the beam again. Let's try to explain the influence line. And before we go, influence line of MC. Okay. Just look at this beam. When I apply the erase this. When I apply the unit load, here, if it's somewhere around here, it's going to create positive moment because you are now having a simple beam, just like this picture, right? So it has to be positive moment. But as soon as the load itself is around here, you see it now trying to push your beam downward. And so if you look at the deflected shape of the beam, it looks like that. So it's a negative curvature. Or if you analyze the beam, you will realize that what you have with this case, okay? In any case, when you have the only load outside of the beam, your reaction here is going to have to be greater than this load P, right? It's a way of a cantilever beam. And your bending moment diagram will end up with a negative value here and a positive value here like this. I mean, shear force diagram. And so your bending moment diagram will look like that. So it's a negative moment. So you see it, the value here, -1, is when we apply the load P here and we look at this value. See, it's a negative moment. So any question? No question, right? So that's it, the influence line. Now you know what it is. Now you know the Muller-Breslau principle, that you can make use of it by creating the qualitative influence line, the shape of the influence line, and you can use your engineering knowledge to further obtain the values of some of the ordinates on the line, and using the similar triangles to expand those values elsewhere, and in doing so obtaining the quantitative influence line as well. So now in comes the next question. What is all the use of this? Okay, so we have the next one. Use the development of the previous example to calculate the values of those design functions. But before we do that, let us go back here and okay, the use of influence line. Okay, well, it can be used to determine the value of those design function, of course, reaction, shear, force, moment, and so on. So now we start from, if the load is a concentrated load, okay? If the load is a concentrated load, now because our influence line is constructed based on the point load, which is equal to 1. So when you have the point load or the concentrated load with the magnitude, you can simply multiply the load with the value of the influence line where the load is applied right away. Right? Because the influence line is constructed by using the point load, which is equal to 1. Now we can multiply the concentrated load that we have on each location with the values on the influence line right away to obtain the values of the design function. That is a point load. Now, let's say if it is a uniform load now, ooh la la, the integration is needed because you see the uniform load is now like this, apply on the influence line that may not be a constant. So we need to integrate to obtain the entire force. So let's say if this uniform load is acting from point 1 to point 2, in order to obtain the design function, you now have to multiply the magnitude of the uniform load with dx and with the height y and perform integral. So when you perform integral y dx, essentially y dx is dA. So that means the design parameters is simply the magnitude of the uniformly distributed load multiplied by the area under which the uniform load is applied. Simple, right? So it becomes just the load multiplied by the area underneath it. Okay. Simple, right? So your next question should be something like, what if the load is not uniform, right? Like a triangle load. Would you like to have that? If you have the non-uniform load, what it means is that W now must go back to the integral, right? And you now have to perform integration for real. So let's not do that, shall we? Or you want it?
No.
That's quick. Okay. All right. So let's not do that. Okay. So that's it. Now we can go back. We have the next one, the placement for the maximum effect, but that will be done next week. So let us go back to here. We are going to use the influence line developed in the previous example to calculate the values of these design functions. Okay. So let's say if that is Mr. M. How do I do this? Mr. M is now weighs 85 kilograms, standing on the tip of the beam. So Mr. M is here. 85 kilogram force. Okay. So now if you want to know RA, for example, RB, right? You just need to go and take the values. I'm sorry, it's just going to be a long stretch going back and forth. The values of RB is 1. Okay. So you multiply 1 with the weight of Mr. M. The value is 1 multiplied by 85. It's 85 kilogram force. D, I think it's 0, right? Because this is 1. So RD is 0. Oh, I'm sorry, this is wrong. We are calculating RB, but 85 is at the tip of the beam, so it's not 1. I'm still not fully awakened. So I have to go back again, sorry. Here, see? It's good that I get it wrong, so you see. Mr. M is here, right? And the magnitude here is 1.5. So this is our influence line. So it's 1.5. the value of the RB, not 1. 1.5 multiplied by 85. I don't have a calculator.
127.5.
Okay, thank you. So let's say 128. Okay. And D now. We go back to this. It's minus 0.5, right? Okay, this graphic is still moving. So the value is minus 0.5 because Mr. M is at the tip of the beam and RD, when we have the load at the tip, is minus 0.5. So we can just go back and finish our work. Minus 0.5 multiplied by 85. So it's like a 42.5, right? 42 minus 42. Am I right? And yeah, it's just a round off number, but when you check the sigma Fy here, it should be 85. Okay. And what else? The let's say for the sake of demonstration, let me put this. Oh, no, that's fine. V, B. Oh, we have VA first, right? VA. VA is, I remember the value. VA is this one, right? Minus 1 up until point A, and we have the load here. So this is minus 1 multiplied by 85. Okay, to ease the pain a little bit, let's take this significant figure out so that you can see that the sigma Fy is indeed 0. Okay. VB to the right. No, I wouldn't remember that. So I have to go back and look at this. Here's my VB why? Oh, it's VC. VB to the right. So our load is here. So it's 0.5, right? Okay. And now VC, right? VC is essentially this one. So again, it is 0.5. You see? 0.5. $42.5. Now we have MA. MA is 1, right? Am I correct? Yeah, MA is minus 1, MB is minus 2, okay? And MC is minus 1. Let us minus 1, 85. So this is minus 85, but the unit is now kilogram meter. MB is minus 1. Oops, sorry. Geez. Minus 2 multiplied by 85. So this is minus 170 kilogram meter. And MC is how much?
Minus 1.
Minus 1, right? Thank you. 85 and minus 85 kilogram meter in the end. Okay. Now, this evidence can be, confirmed when you draw the shear force and bending moment diagram, right? These values should match. Because let's say if this is your beam, your shear force diagram is minus 85. All right, comes down here. If you really want to calculate the reactions, the RB here is 85 multiplied by 6 divided by 4, right? Which is essentially it's 127.5, and it goes back. This line is 127.5, right? So this is 42.5. So that's your, sorry. So that's your shear force diagram. Okay. And RB, it's that, right? RD, that's a downward force there. VA, see? VA is here. So that's minus 85. VB to the right. Now we move on to the right. So we meet the positive value instead of the negative one. If it's to the left, it's minus 85. If it's positive, if it's to the left, it's minus 85. If it's to the right, it's plus 42.5. VC is around here at midspan, so it's that value. See? And now, bending moment diagram. When you have 85 there, of course, this is the negative moment. Minus 85, right? And it goes back to 0. So MA, oops, sorry, not minus 85. What's going on with me? It's 2 meters, right? So that's minus 170. That's your bending moment diagram, correct? And here, let's change the color a little bit. MA is this point, minus 85. That's MB, right at the support. And MC is somewhere in the middle, still negative. See, it matches. But instead of, let's say if you have so many loads and it moves around, instead of having to go back and create the shear force diagram, bending moment diagram for each case, we can just use the influence line to obtain the values right away. Is there any question? No. Okay. And let's say if you continue to have maybe Miss Q weighs 45 kilograms running after Mr. M to the 0.5 meter left of B. That means Miss Q is now perhaps here. You just add the value because now we have RB due to Mr. M, right? And when you have Miss Q, you just add the values up to the values that you already have. So we are running out of time, so let me demonstrate some. So RB will become 127.5. Now plus, because Miss Q is 0.5 meter left of B, we need to go back here and look at the values from the influence line. Okay, left of B here, this is 2 meters, right? So at this location, 0.5 meters. So the value is not 0.5, so let me remove that. Just want to point it out. So the values will become 1, right, which is this. And you use the similar triangle ratio. So this is going to be divided by 4, right? Because that's a triangle. And now this becomes, because it's 0.5 to the left, so this is 4.5. So the ordinate of the influence line at that location is 4.5 over 4, right? And now we go back and, sorry. So it's 4.5 over 4 multiplied by the weight of Miss Q. And there you have your RB. Okay?
178.
Oh, the answer, right?
Yes.
Yeah, it's 128 kilogram force. Okay, and we are running out of time, so just to demonstrate this, let's say I'm going to add Mr. X. Mr. X also weighs 70. Follow Miss Q until 1 meter, right? Oh, just something missing. Maybe right of the support here. Say put Mr. X around here. Mr. X, but I think you have the idea now. So RB will now become 178 plus, if he's 1 meter, we go back here, 4 meters here, right? If he's here, this magnitude will be 1 multiplied by 3/4 or 0.75, right? Okay, so whatever the number is. So it's about 231 kilogram force. That's sorry, that's not kilogram, meter. Kilogram force. Okay. Say with Miss Q. Here would be with Mr. X. All right. And now if I continue on by adding the uniform load of 200 kilonewton. Oh, wait, so if it's kilonewton, so that means I have to multiply all what I have done with G force, right? That's okay. So let's say if this the values RB, if there's a uniform load alone, the RB would be uniform load RB would be the total area multiplied by 200, right? So we now need to go back to calculate the area of the inference line. And notice that this inference line has only positive area. When you apply the unit load, when you apply the uniform load throughout the beam, let's say R for RD, that would be negative area and positive area because the uniform load here will produce the upward reaction. The uniform load here will produce the downward reaction. So you must account for the positive and negative values of the area as well. But for the RB, the area would be, the length is 6, the height is 1.5, right? So here it would be a half of 6 multiplied by 1.5. Okay. Essentially, that's 200 multiplied by 3 multiplied by 1.5. So it's 900 kilonewton. Say, let's demonstrate RD. It's 200, right? The load. The area is now a half of, let us go back, sorry. See, we have the positive area here. Oh, I should do it on this one. We have the positive area here. And we have the negative area here. So you must account for that. Okay. So, right, we go back here. We have the positive area of a half multiplied by 4. Oops, sorry. Multiplied by 4, multiplied by 1, minus the negative area of a half multiplied by 2, multiplied by 0.5. Huh? So that will give you the reaction of RD. Okay. But okay, let's see, finish this. This is 2, this is 0.5, so it's 1.5 multiplied by that, so it's 300 kilonewtons. Okay, for example, I think you get the idea. We don't need to do the repeated actions to get all the numbers for everything. So if you wish to do so, I think it's available in the last year's clip as well, but this year's clip, I think I have done a better job in explaining the some of the sections than the last year. So it's like a trade-off, but you have the values from last year, but you have better explanation this year. So, okay. Any question then? That's it for today. Hello.
No questions, sir. I'm still okay.
You're still okay, right?
Yeah.
Of course you are. How can you not be okay?
But I have to look back.
You speak as if the class is like a disease. You know, okay, so let me stop the record first.